Now here, find the power developed across the 10 ohm resistance using the Norton's theorem for the figure shown below. This is the load resistance, and we are interested in the calculation of power developed across this load resistance. Formula for the power is IL square into RL. This indirectly we are interested in the calculation of the current first. What is the first step? Remove the load resistance and redraw the same circuit and short the output terminals for the calculation of the Norton's equivalent network. Is it right? I will write the same. Removing load resistance and shorting output terminals. We get. If we are removing the load resistance and if we are shorting the output terminals, how will be the circuit? This will be the figure. This will be the figure. Here is A point. This is B point. Here it is 3 ohm. This is 2 ohm. This is 6 ohm. This is 4 ohm. This is 2 ohm. This is 5 ohm. And it is 20 ohm. This is plus and minus. Now, short this output terminals. Now, what we have done, we have removed the load resistance, we have shorted the output terminals, and we have redrawn the same circuit. Now, calculate current in this short circuit, which is the Norton's current. Use any method. You can use the direct inspection method, mesh analysis, nodal analysis, whatever. Being the first problem, whatever I have used in the explanation, I will use the similar method. Means I will use the nodal. You can use the mesh. This is mesh 1, mesh 2, or direct inspection method, or whatever. This is node A having its potential VA. This is ground node having its potential 0. This is the first branch having its current I1. This is the second branch having its current I2. And this is the third branch having its current as IN. And we are interested in the calculation of the IN, which is the Norton's current. Now what we will do? We will apply the KCL at this, and we will simplify the KCL. We will find out the VA first. I will write the same. Applying KCL at node A. We get. If we are applying the KCL at node A, how is the equation? Incoming current is equal to outgoing current. Incoming current is I1 is equal to I2 plus IN. We can use any method for the calculation of IN. For example, I am using this method, which is the nodal analysis. How is the I1? 0 plus 20 minus VA. This 20 minus VA divided by resistance, that is 5 plus 2, which is 7, which is equal to 7, which is equal to I2 is the current in this branch, VA divided by 4 plus IN. IN is the current in this branch. It is VA. We are traveling from positive to negative minus 2 divided by resistance of this complete branch, that is 3 plus 6, which is 9. Now simplify this equation. It is 20 divided by 7 minus it is VA divided by 7, which is equal to is VA divided by 4 plus it is VA divided by 9 minus it is 2 divided by 9. That is the equation. If we are simplifying this equation, I will shift this VA on the next side and I will take it as a common. Then it is 1 by 7 plus it is 1 by 4 plus it is 1 by 9. This value is equal to, I will shift this constant to the left hand side. This it is 2 by 9 plus it is 20 divided by 7. Work out this calculation and find out this value of the VA. Otherwise, value of this bracket and this value. I am expecting the answers from your side. Yes, anyone? Yes. Saurabh, unmute yourself.
0.50 VA.
0.5
0.
VA.
Equal to 3.07.
3.07.
07.
Is it right? Therefore, this VA is equal to, this is 0.5 divided by, this value is 3.07 divided by 5. How much is, 0.5. How much is the value of VA?
6.14.
6.14 volt is the value of VA. If we know the VA, we are interested in what? We are interested in this current, which is IN. Therefore, the Norton's current is equal to this value. VA minus 2 divided by 9 is VA minus 2 divided by 9 is the Norton's current. Means it is 6.14 minus 2 divided by 9 is the IN, which is equal to. Yes. Ruchira, unmute yourself. Yes.
0.46.
0.46 amperes is the IN. This is right. Now, if we know the IN, we can find out the value of RL. And for the calculation of RL, we will remove the load resistance and we will remove the sources by the respective internal resistances. I will use the same. For the calculation of RL, we will remove load resistance and all sources are replaced by respective internal resistances. Is it right? Now, how will be the figure for that calculation? I will draw the figure here. I will draw the figure here. In this case, we are removing this load resistance. The source will be replaced by its internal resistance. This here will be the figure. Here will be the circuit, something like this. It will be this resistance. Here is resistance. This is another resistance, and finally, this is the last resistance, and it will be replaced by its value. It will be replaced by its internal resistance. It will be replaced by its internal resistance. These are the sources. Now, how is the case? This is 3 ohm. It is 6 ohm. This is 4 ohm. This is 2 ohm. And this value is 5. Is it right? In this case, we have to find out now the series and parallel combination, and we have to find out the value of its resistance between the terminals. Now look at how is the combination. These two are in series. There is the resistance. This is the next. And this will be the next figure. It is A point, this is B point. This is 3 ohm. It is 6 ohm. This value is the 4 ohm. And its series combination will be 5 plus 2, that is 7 ohm. This is right. The next, these two resistances are in parallel combination. Then how will be the next figure? It will be something like this. Here is the A point, this is B point. Its parallel combination is this value. Here it is 3 ohm, this is 6 ohm. And this value is how much? Parallel combination. 7 is parallel with the 4.
2.54.
2.54. Now therefore, Rn is equal to, or Norton's equivalent resistance is equal to, I guess it is 3 plus 2.54 plus 6, which is equal to, I guess it is 11.54 ohm is the Rn. That is Norton's equivalent resistance. And finally, if we know IN and Rn, then complicated network is replaced by Norton's equivalent network. Norton's equivalent network. And how will be the Norton's equivalent network? This is the Norton's equivalent network. And reconnect the load resistance which is removed in the first step. This value is 11.54. This is the Norton's current which we have calculated in the last step, which is 0.46 amperes. This value is 0.46 amperes. Reconnect the load resistance which is removed in the first step. What we are interested in the calculation of 10 ohm. 10 ohm is the load resistance and we are interested in the calculation of the power. This value is the 10 ohm. Now, calculate the load current first. How is the case? You can make it as a current division rule or just copy the formula. One and the same thing. This is 0.46 total current into resistance of the opposite branch 11.54 plus 10. That is IN into Rn. How much is the Rn? 11.54 divided by Rn plus RL, which is equal to total current into resistance of the opposite branch divided by resistance of both branches, because we are interested in this current which is the IL. You have to mention the IL in the figure also. How much is the value of IL?
.24.
0.24 amperes is the IL. And if we know the IL, we can find out the power delivered. P is equal to IL square into RL, which is equal to 0.24 its square into RL. RL is the 10. 0.24 square into 10. Sorry, 2.24 square into RL, that is 10, which is equal to how much is the power delivered to the load?
.576.
It is 0.576 watt is the power transferred to the load or power delivered to the load, and thus we have calculated by using this theorem, which is nothing but Norton's theorem.